Hey guys, how are you? Today we are going to discuss a new topic about algorithms. We are going to discuss iterative algorithms and how we can prove its correctness. But before going to this stage, we need to understand some mathematical terminology. So, if we talk about arithmetic progression, for example, let me get it into here. Yeah, I have this example. If I want to get the sum of n numbers by arithmetic progression, it is 1 plus 2 plus 3 plus 4 plus blah 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 till n is equal to n plus n multiply n plus 1 over 2. How to prove this? If I take n of n equal 1, then the sum is equal 1. Normal, like 1 multiplied by 1 plus 1 is 1 multiplied by 2 over 2 basically is 1. So if we take n equal 2, so I need to do summarize of these two numbers. So it's 1 plus 2 equals 3. If I take the right hand side, or RHS, is gonna be 2 multiplied by 2 plus 1 over 2. 2 plus 1 is 3, so 2 multiplied by 3 over 2 is 3, which is equal to the left hand side. If we take n equals 3, so basically it's gonna be 1 plus 2 plus 3, which is 6, which is equal also to 3 multiplied by 3 plus 1, which is 4. 4 multiplied by 3, it's 12. 12 divided by 2 is 6, and so on. But if we are going to do this for all the items or all the numbers, then when we are going to stop, when we can say this algorithm or this equation is correct, then we will jump into something called mathematical induction. The mathematical induction is saying, if we have something like this one, we can prove it's correct for one step, for basic. Let me get the pen. We will have something called base case. Okay, we will prove that this is correct for base case, and then we will have a case x or k or whatever k number, like we will assume in this situation it is correct, and then we try to prove that k plus 1 is also correct. So if we prove this one, so we will prove all the series, because I proved the base case, which is 1, then I took any number k here and I assume it is correct. Then if I can prove that k plus 1, sorry, k plus, if I can prove k plus 1, why it is not help me? If I can prove k plus 1 is correct, that means if I start by this and I proved any number is correct, if a number is correct, the next number is correct. So I proved 1 is correct, and then 2 by this assumption is also correct. And as long as 2 is correct, then by this assumption, if I have k is correct, then k plus 1 is correct. So 3 is gonna be correct. If I take 3 is correct, then 4 is gonna be correct. Or if I took 4 is correct, then 5 is gonna be correct. So all the series will be correct. So let's try to prove it, and let's see how to do it. In our arithmetic progression, we will assume our base case is 1 when n equal 1. So if this is the case, the sum, or the left hand side will equal 1, but the right hand side will be will equal 1, sorry, 1 multiplied by 1 plus 1 divided by 2, which is equal to 1 multiplied by 2 over 2, which is equal to 1. So we proved the base case, which is this part. Then we need to assume that k is correct, and we try to solve it for k plus 1. So we will assume that for 1 plus 2 plus 3 plus 4 plus dot 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 plus k is equal to what we are talking about, k plus 1 over 2. We will say we assume this is correct. We assume this is correct. Then our homework is to prove if this is correct. Then we need to prove that this is also going to be correct. But instead of k, we will put k plus 1. That means we will add here k plus 1, and here instead of k it will be k plus 1. So and this k also will be k plus 1. So this is going to be our right hand side, and the other one is going to be our left hand side. Okay, so now we are saying that we have that from 1 to k, the summation is k multiply k plus 1 over 2 by assumption, and we need to see how to prove the second point, which is this one. This we are going to do what we are going to do. So I'm gonna get this one and substitute it with the value that we get it from the above assumption. So basically these are the same, right? No change. So our left hand side in this case is equal to this part, which is the substitution, plus that part, which is the additional term to the arithmetic progression. Okay, let's try to simplify the left hand side a little bit and keep the right hand side aside. So we will try to take k plus 1 as a common factor. So our left hand side will take k plus 1 as a common factor. Then what we will have here, we will have here k over 2, we will have this one, k over 2 is going to be here, and that element will be 1. Okay, let's try to simplify it a little bit again. So it's gonna be k plus 1 as a common factor, and then I'll make a common denominator, which is 2. So it's k over 2 plus 2 over 2. 1 is equal 2 over 2, which is equal k plus 1 multiply by, here it's gonna be k plus 2 over 2, right? Okay, so this k plus 2 over 2 is basically equal we will put the k plus 1 and then we are talking about k plus 2 over 2 basically is k plus 1 over 2, which is equal exactly the same as the right hand side. Right? So we prove it. So we prove the base case. Cancel this one, we don't need it. We prove the base case, which is at 1, and at any moment of time k, at any number, at any term k, we assume it is correct. So we prove that k plus 1 is correct also. That means if 1 is correct, then by this terminology 2 is gonna be correct, and once we prove 2 is correct, then 3 is gonna be correct, and because 3 is correct, then 4 is correct also, so and so on. So by mathematical induction, we say if we prove the base case and we take any element k in the series, we'll say k is less than whatever number that we are going to do the summation. If we are doing summation till n, so n is greater than or equal k. This is our assumption. So if we take any number k less than n that we are talking about, and we prove that k plus 1 is correct whenever k is correct, then we do this, we prove the whole thing. We don't need to iterate it anymore. The iterative or the iteration is happening by default. So if I go to our mathematical induction in more organized way, these are the steps. The step 1, prove that the algorithm or the problem is working fine for the base case. Step number 2, assume that k, which is less than n, is correct, and then step number 3, try to prove it for k plus 1, and at the end conclude your conclusion or conclude your proof. And this is another example. If we are talking about same thing, if we are having a progression that has 3 plus 6 plus 9 plus 12 is equal till 3 of n is equal 3 n plus n plus 1, 3 n multiplied by n plus 1 over 2. So the first base case is gonna be n equal 1, so 3 multiplied by 1, the left hand side is gonna be 3, right hand side is gonna be 3 over 1 plus 1, which means 3 multiplied by 2 over 2, which is 6 over 2, which is 3. So the left hand side for the base case is equal to the right hand side. So we assume it is correct for the k element. Okay, here is, we say n is greater than k. So if by assumption k is correct, so this is correct, and then we try to prove it for n k plus 1 from the assumption. The left hand side is gonna be 3 plus 6 plus 9 plus 12 plus till 3k plus 3 multiplied by k plus 1. This is what we need to prove. And then in the right hand side is going to be 3 multiplied by 6 k over 1 k plus 1 multiplied by k plus 1 over plus 1 over 2. From the mathematical hypothesis or the assumption, we took this part and we do the substitution. So the left hand side is going to be this plus 3k plus 1, and right hand side kept unchanged, we are not going to touch it. So here again I took the k plus 1 as a common factor, so the remaining is gonna be 3k over 2 from this part plus 3 here, so which is this part, and then we have 3. I'll take the 3 as a common factor as well, so it's gonna be 3k plus 1 multiplied by k over 2 plus 1. The 1 is equal to 2 over 2, so I can take common denominator. So I took the 3 here, I took also the common denominator 2 as common factor outside, so 3 over 2, and the remaining is gonna be k plus 1 multiplied by k plus 2, which is k plus 1 multiplied by k plus 1 plus 1, which is the right hand side. So by conclusion, our conclusion is, by process of the mathematical induction, this series is correct. So why we are doing this? Because as you see from this analogy, you can see this is an group of iteration. We get 3 plus 6 plus 7 plus 9 plus 12. So this is a pattern of iteration. In algorithms, we have these for loops, we have this iteration, we have something called iterative algorithm, that an algorithm that depend on for loops and while loops and do while loop, or whatever loop we are going to use. So we need to do solution or an algorithm for doing the factorial. Factorial basically, factorial of 7 means 7 multiplied by 6 by 5 by 4 by 3 by 2 by 1, or if we take it by the other side, like 1 multiplied by 2 multiplied by 3 multiplied by 4 multiplied by 5, 6 and 7. So this is my factorial. I want to make a program to solve this issue for me. So I'll open IntelliJ. I have already wrote the algorithm or the function in this case. So basically I pass to the function x, and I define a double factorial or facto parameter as facto, and I give it to 1. If the x that I am passing to the function is equal 0 or 1, then return 1, because factorial of 0 is equal to 1, factorial of 1 is equal to 1 too. Otherwise, define a variable I, which will start by 2, because 0 and 1 is already gone, and I is less than or equal x, then I plus plus. What I need to do, I define this temp variable or facto, and I will say my factorial is equal to my current factorial is equal to my previous factorial plus 1. So if I am here, it's 1. When I come to this for loop, I equal 2. So factorial of 2 is gonna be 1. The new factorial is gonna be 1, which is this one, multiplied by 2. So factorial of 2 is correct 2. And then if we pass x as 3, so the factorial is gonna be, this for loop will happen twice. So in the first iteration factorial is going to be 2. In the second iteration 2 multiplied by 3 is going to be 6. In the third iteration, if we are going for third iteration, it will be 2 multiplied by 3 multiplied by 4, and so on, multiplied by 4 multiplied by 5 multiplied by 6, and so on. So if, for example, I pass, let me put a breakpoint here so you guys are gonna follow with me what's going on, and I'm gonna pass in this, I'm gonna call this function with a equals 7. So let's see what's going on. Oh, sorry, I need he solved it straight away. Let's go by debugging first. Yeah, by debug, in the debugger, yeah, see here facto is equal to 1, okay, and I equal to 2. So if I go to the next step over, now facto is equal to 2, and he's going to iterate again the for loop, okay. I equal, in this situation I equal 3, and the old factorial is gonna be 2. So factorial of 3 is basically 2 multiplied by 3, which is 6. If we iterate it, so now factorial has become 6. If we go again to the for loop, I equal 4, okay, we enter the for loop, we still less than 7, which is our ending condition, less than or equal 7, so we are still in the loop. So 6 multiplied by 4, 24, which is the correct factorial. Factorial of 4 is 24, which is 4 multiplied by 3 multiplied by 2 multiplied by 1. Let's go over again. So factorial is 24, go over again, 120, go over again, 720, which is 6, and then 7, it is the last condition. Now I is gonna be greater than 7, which is not gonna enter the for loop, and we will go for the return immediately, and return now is having the last factorial, which is 5040. So the algorithm seems working, but we need to prove it. We need to prove it by our methodology. It's not by iterating it 100 times, million times. But if I do it million times, still it might fail in million and one time. If I do it billion times, it might fail in the billion plus one time. So we need to have this mathematical induction way to prove it. It was gonna work for every cases, for all the cases. Okay, so we are going back to our terminology here. This is the algorithm, just put it here, and then we will do our mathematical induction. In this algorithm, if you can see, we have two base cases. We have this if statement in the beginning that was asking if x equals 0 or x equal 1. So we need to prove that our algorithm work correctly for both cases. So what will this algorithm give us a solution or a result if x equals 0 or 1? It's gonna give us 1. So our base case for x equal for x equal 1 or 0, the result is 1, which is correct for both the base cases, because factorial of 0 is 1, factorial of 1 is also 1. So by doing this, we make sure that our algorithm is working fine for this base case. Then we will assume that our algorithm works fine for a k, which is an integer number less than x, the number that we are going to test. And then the algorithm we assume by assumption that the algorithm works fine for this case. That means factorial k is equal to 1 multiplied by 2 multiplied by 3 multiplied by blah 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 till k. Then we need to prove what is the behavior of our algorithm and how it will calculate k plus 1. So in our algorithm, if we prove this is correct, so the correct factorial of k plus 1 is basically 1 multiplied by 2 by 3 by 4 till k, and then multiply by k plus 1. And we assumed from assumption that this is correct. So our assumption is saying we need to prove that our algorithm to calculate factorial of k plus 1, by the way, the factorial sign is exclamation mark, so we need to prove this is correct. Okay, that's fine. From assumption this is correct, and we need to see the behavior of our algorithm. The for loop is showing me that my new factorial is equal to the old factorial plus the current number plus k plus 1, which is what we are talking about here. The new factorial is equal to the old factorial multiplied by the new number k plus 1, which is exactly what we are doing in the for loop. The new factorial is equal to the old factorial, which is k multiplied by k plus 1. So k plus 1 factorial is equal to the old factorial, which is k multiplied by the k plus 1 number. Okay, so our factorial is working fine for the case of k plus 1 as well, because at any moment of time our factorial is factorial of k plus 1 is the factorial of k multiplied by the new item, which is k plus 1. So we prove this one. So the last part, we need to do the explanation of our methodology. By the process of mathematical induction, the algorithm calculates the factorial correctly for the two base cases, and also by the mathematical induction hypothesis, which is k, the algorithm works fine for the to calculate correctly the factorial. So by doing so, we have an idea about how to prove our iterative algorithm correctly. We can do it by trial and error, but as I said, if I do this algorithm 100 times, then it might fail at 100 plus 1. If I do it 1000 times, it might fail at 1000 plus 1. If I do it million times, it might fail at million plus 1. So by the mathematical induction, the mathematicians showed us a methodology to prove it for all the numbers that you are going to test, as long as you prove it for the base case and take the k plus k hypothesis and then prove it for the k plus 1. And this is how we prove the correctness of the iterative algorithm. So basically, summary of our lecture today, we had two examples basically about mathematical induction and what does it mean and why we are using it. And then we talked about iterative algorithms. Iterative algorithm is nothing but an algorithm that we use for loop, while loop, do while loop, or whatever iterations we do number of iterations to get our solution. And we showed by mathematical induction how to prove the correctness of an iterative algorithm. I hope this session was light and you guys enjoyed it. I'll upload as usual this document here, and also the code is I'll upload it in the description. I hope you enjoyed it, and follow me in the next sessions inshallah. Thank you and good luck.